everybody. My name is Daniel Weimer. I'm from the Volkswagen Data Labs, and today I have the pleasure to present some of the work in the field of deep convolutional neural networks with a focus on industrial applications. So, right at the beginning, a question: who is actively working in his daily work with deep learning? Cool. So, I basically start somehow from the beginning. So I will explain a little bit the basic pipeline of machine learning because this motivates deep learning at all. Then I want to set a focus on deep concepts in the field of industrial inspection, one of the most important things in manufacturing. I present some experiments, results, and which is very important limits of deep learning. And finally, I want to conclude. So, the traditional machine learning pipeline, if you want to detect a car, for example, what are you doing? First of all, you have to find an appropriate set of features to describe the car, let's say the shape, the color, or whatever. And then you take these features and feed it into a classifier. This classifier is trained with historical data, standard approach. What might be the next step? The next step, or let's see the features first of all. You can, for example, use the histogram of ordinary gradients, which is a gradient-based method. You can use the most or a very famous algorithm SIF, or you can use, for example, wavelet-based features, which are also a good tool for face detection. The same holds for 3D. So these are all low-level features. Why low-level? Because you use basically the gradient information, which is a very basic information. What happens until 2012 was, based on this low-level feature extractor, people put a mid-level feature extractor on it. So this means they took the low-level features, and based on these low-level features, they have an additional layer with some kind of k-nearest neighbor search, for example, or an autoencoder or things like that, to transform the low-level features into a mid-feature level dimension. And then took these mid-level features to feed the classifier in the same fashion. This was state-of-the-art until 2012. But there's one problem with it. First of all, it still depends on a handcrafted feature representation. So this means an expert has to define these features, so this means it is a very expert-driven kind of machine learning approach. This took a lot of time. It took a lot of experts and a lot of time to find the best set of features for a given problem. But so we are now in the era of deep learning. Maybe anywhere in the universe there might be a better set of features compared to the features we already have. We now have the techniques of deep learning to find these features. So let's do it. And I want to here describe why it makes absolutely sense. Take the traditional approach and let me say, I call it better approach. Machine learning, this huge technique of machine learning, this very powerful technique, is only applied in the last step when it comes to the model generation, when it comes to build the classification model. All steps before are completely expert-driven. The generation of the features, for example, is expert-driven. At least, approximately no machine learning is included here. Machine learning is only included in the very, very last step, even in the better approach with the mid-level features. In contrast to that, deep learning also includes the generation of features into the learning approach. So this means the bases are raw data, and we learn the features and the model in one closed framework. This is the basic idea of deep learning. And another example, what might be the, let me say, the ultimate result of a machine learning algorithm applied on this image. So, for example, you see some persons, you see a ball, you see it in grass, and the ultimate result might be, it is the 8th of July in the Maracanã Stadium, and Mario Götze scores the 1-0 for Germany in the 118th minute and make Germany to the champion of the world in football. So, but only based on this image, the ultimate result might be 4 persons playing football in a stadium. So this is basically the information which is in this image. Imagine standard algorithms. So standard computer vision algorithms. You need very different kinds and a lot of algorithms to find all these different things in an image. You need, for example, a Hock descriptor to calculate the persons. You need, for example, a color histogram to see that it is grass. You need, for example, a half transformation to find the ball, which is a round piece of object. And deep learning is able to calculate all these different steps in one closed framework, starting from raw data, raw pixel data, and transform it in a nonlinear fashion, we will see this in a minute, to more complex features until to the, let's say, to the most or to the highest kind of information, and this is basically the content of the image for person playing football. So the basic question of deep learning is, can we learn powerful features directly from data without the need of human interaction, without the need of a process expert who describes features manually? And the answer is yes, we can. We can use deep learning. And let's see. Before I go more into the details, I want to have a second motivation for deep learning. So why do we need actually a new paradigm in artificial intelligence or machine learning? We have powerful techniques, we have great techniques, statistical learning theory, support vector machines and things like that. Why do we need deep learning? Why do we need a new paradigm? And the answer is this slide. I borrowed it from Andrew Ng. Some of you may know him. He's the Andrew is a professor for robotics and machine learning at Stanford University, and maybe some of you know his famous mock course on Coursera machine learning. So if you don't trust me, trust him. The basic thing is, or what you see here is the amount of data, let's say the amount of training data and the performance you can gain on a training set, on a test set the algorithm has not seen before. And what you can see is that with a rising amount of data, most learning algorithms are saturating with respect to performance. This means even if you feed in more data into the training phase, you will have no benefit with respect to performance. In contrast to that, deep learning scales with the data. As more data, as better the models. And in the era of big data, we all talk about big data. This is the key. Deep learning is the key because it scales with the data. This is very, very important information. Let's go a little bit more into detail, and basically deep learning, or the basis of deep learning is basically a neural network, which is, if you also take the perceptron into account, which was born in the 1950s, which is approximately 60 to 70 years old. What happens in a neural network? You have, let's say, an image, you calculate a set of features, for example, the Hawk features we've seen before, or any kind of features, and this is your input layer. You have additionally a nonlinear layer, which maps the result to an output layer. What happens here is each so-called neuron is connected with all the neurons in the hidden layer, and these kind of weights are simply called neuron weights. They have a value between 0 and 1, and right at the beginning you initialize these weights randomly, and with training these weights became changed and learn the structure in the data. Okay, so far so good. You have additionally a bias term here, but let's skip it for now. What is the basic idea of deep learning? The first basic idea is simply to add more hidden layers. Why? Because a hidden layer is a nonlinear transformation, so it makes definitely sense to have more than one nonlinear transformation. But what is the what happens is you take the raw data and from stage to stage you transform it in a nonlinear way. So the result of this layer is a nonlinear transformation of this layer, and this means a more complex representation. And you can see here, so you feed in an image. In the first layers you learn some basic kind of features, let's say wavelet features, let's say gradient features. In the mid-level features in face detection you, for example, learn parts of a face, let's say an eye, a nose, a mouth, an ear, or something like that. And in the high-level hierarchies you learn complete faces. And this is basically the idea. You transform raw data from basic information into very, very high abstract level information. And how do we train this kind of networks? This is the basic thing. We have to train these networks. And the basic idea, or the basic algorithm which is used in neural networks for that is backpropagation. What happens here is, in training you start with a, let's say, randomly initialized network, and you feed in training examples and training examples, and you propagate forward through the network, and you know that a defect is a 1, and you expect a 1, but basically the network says 0.8, so you make an error of 0.2. What happens now in the basic backpropagation algorithm is you take this error and propagate it back. I mean, maybe the most of you know this kind of algorithm. It's called backpropagation of errors. But in a deep network, this doesn't hold. Why? Because of the depth of the network, the gradient became smaller and smaller and smaller, and the network is not able to learn an appropriate representation of the feature. So this means you have no benefit by adding more layers. This was the problem until 2006. It doesn't make sense to add more layers because the network was not able to learn. And the problem is, as I mentioned before, the vanishing gradient problem. So when you go back, the gradient vanishes. And now the question is, why is deep learning now so popular? Why does it work right now? And it works because of two very simple ideas. And I want to introduce these ideas. So the first idea introduced by Hinton was, instead of learning a complete network, we split the network. So this means we take this layer, the first two neurons, and simply map the input layer, or take the input layer also as an output layer. This is called the autoencoder. So this is a simple autoencoder. So this means instead of learning the complete network at once, we split the network. And then we are able to learn a very, very small network in fractions. So then we split this neurons, then the other neurons, and so on. And we stack it finally together. And then we have a very, very good pre-initialized network who basically knows the idea, what it has to learn. And then we can use fine-tuning on the complete network. This is the basic idea of 2006 paper of Hinton, which was somehow, it was published in Nature, and it was somehow the starting point of deep learning. It was one of the first times that people were able to train networks with millions of neurons. Today, we don't use this kind of stacked autoencoder training anymore. I think there will also be a renaissance in this, because, sorry, I have to skip that, because we can train this network with unlabeled data, and in real-world processes, labeled data are very, very expensive, so you can train this network with unlabeled data. This is a very, very powerful thing. Today, we basically use supervised data, so this means we have a training set and the label. Instead of the stacked autoencoder, we use techniques from the 80s. It is called dropout, for example. So this means we are now able to train a network because we drop out randomly neurons during training. So what happens is, instead of learning all the neurons, we switch off randomly some of the neurons. Let's say, for example, so we take an example, switch off some of the neurons, which is a condensed model, and then go back and do the backpropagation. So dropout is now one of the key techniques. The other technique is regularization. I don't want to elaborate on this right now. And activation function. The activation function is the key to avoid this kind of vanishing gradient problem. So this is the way how deep nets are trained today. And I only talked about deep neural networks so far, but the application I want to present you is an image processing problem. So with fully connected standard neural networks, we end up in a problem. Why? Because when you want to analyze an image in a standard formulation, you have to connect each pixel in an image with each neuron. This is the definition of fully connected. Each neuron is connected with each neuron, or each pixel here in this case. And this is a problem because, say, we have an image of 1,000 by 1,000, and we have 200 neurons, which is not so much. We have 200 million neurons. So 200 million neuron weights, 200 million parameters in the first layer we have to optimize. This is definitely too much. So what happens is, instead of connecting each pixel to each neuron, we take a group of pixels and map it to one neuron. It's basically a filter, so it is a convolution. And this was a basic idea from Jan LeCun in '89. And this is why it's called deep convolution net, because grouping pixels and shifting this block over the image is, as I mentioned before, a convolution. And this is this is where the network had its name from. And as you can see, you can drastically or dramatically reduce the amount of parameters. Before we had 200 million, now we have 100 parameters per neuron, which we have to optimize. I don't want to talk about weight sharing, but weight sharing is another very important thing in deep learning. So, some of you may know this structure. It's called a deep convolution net. So you have these filters that result in some kind of feature maps. And I want to now go for a few minutes a little bit in detail with respect to this. Each convolution network consists of 3 stages: a convolution stage, and pooling stage. You don't have to use pooling. This is where it's here -9. And finally, the nonlinear activation. Nonlinear activation is the key nonlinearity in deep network. So let's see the details. So in the convolution stage, you define a set of neurons, and I mark these guys here a little bit in bold because these are design hyperparameters. So what is a hyperparameter in contrast to a parameter? So a parameter is a neuron weight. This means we learn these neuron weights during training. This is a parameter. And a design hyperparameter is a parameter we have to define in advance before we start with training the network. For example, so basically the architecture of the network. We have to define a number of neurons, the number of layers. This is a hyperparameter. We tell the network, you look like this. This is why this is called hyperparameter. In the convolution stage, we have, for example, k neurons learn n by n filter. So the number of neurons k and the filter size n by n, which we have seen before. We have to define the step width, for example, of the pixel. So we have to shift this filter over the image. So this is all the stuff we have to define in advance. The convolution stage is the first stage. In the second stage, we apply pooling. And the pooling stage, as you can see here, so the result of the convolution stage is then pooled. So you see the information is reduced. How this happens? Let's say this block here is the result of the convolution stage. And then we simply divide it in 2x2 blocks, overlapping by 1 pixel, and just take the maximum value in the small block. So I will show it here. So as you can see here, we group it by 2x2 pixel, and the maximum value is 7, so we just take the 7 into the next step. So this is basically pooling. It's a very, very, very easy idea. And in the last step, we have the activation. So this kind of feature map is then multiplied with the activation function. Here you can see 3 different kinds of activation functions. The first one is called the sigmoid function, which is the most traditional one. It's a logistic regression, basically. You have a tangent hyperbolicus, which maps the space into into values between 1 and -1. Here you map it between 1 and 0. And you have the rectified linear unit. And what is the difference between all these activation functions? I don't want to go too much into detail, but one thing is very important. The red one is the real activation function. So this is really the activation. The blue one is the gradient you need for backpropagation. And what here is very important, when you see the dotted line of the sigmoid and the tangent hyperbolicus function, you see that for very, very high values, let's say here, or for very high negative values, you do not learn anything. These values will not have a contribution to the overall result. This means if the activation is very high, you learn nothing because you change nothing. In contrast, the rectified linear unit for positive values always learns. And this is this is a key point in deep conference or in deep learning in general, introducing the rectified linear unit. So this is in many cases the method of choice or the activation of choice. And let's see a little bit more, or let's go a little bit more into the application. So we now have introduced deep confidence and used deep confidence for that. First of all, I want to show you the problem. So here you see different surfaces. This is a public available database, so if you want to download it as well, I can share the link with you, no problem. You see different classes, different kinds of defects. You see that in many cases it's even hard with the human eye to detect the defect. I will show you the defects here. So the question here was, can we train one single network, one single deep convolution network to classify all these different defects in all these different classes with one single network? This is the basic idea. And if you think about that, if you have to solve this problem with a standard computer vision algorithm, it is extremely complex because you have different kinds of backgrounds, different kinds of defects and things like that. So, as I mentioned before, defects occur with varying size, orientation, shape, so a scratch can have any kind of orientation. And the question is, how do we apply deep learning to that? So, I just want to spend 1 minute. It's basically a classification problem. Most of you know classification. You have a good class, you have a bad class. What you're trying to do is you try to find a hyperplane which separates both classes, and then you will know this, or then you have this kind of example the network has never seen. You compare it with a hyperplane, and then you can say it's good or bad. We learn from historical data. Supervised learning at its best. So it's pure supervised learning, okay? So let's go a little bit more into the details. The first thing you have to do is the preparation of data. How do we show the network the data? In this case, in the first step, we do not take the complete images, we sample from the images. So this means we extract patches, and we know, because we have the label, that specific patches are in a defect area or in a non-defect area. This is called block extraction. In the second step, we use standard augmentation algorithms, so we rotate the patches, we mirror the patches, and things like that, because then the training set is higher, and we are, it's easier for us to deal with rotation and translation algorithms. In the last step, we fuse everything, and this is very important. If you have a multi-class problem, shuffle the data. If you learn class by class, you will end up in fancy problems because of the gradients. So shuffle the data. It's a standard approach since the 80s. Shuffle the data when you use these multi-class things. And then we feed in these extracted blocks into the convolution network and train the network. So now, one thing was very important, and it is still important. What is the best architecture to solve a given problem? This is a key question in deep learning. You have so much hyperparameters. You can change the number of neurons. You can change the number of layers. How many layers I want? You can change the number of filters and things like that. And I think it's current research or it's still ongoing research. What we have done was the following. We defined the size of the filter you have seen in the convolution space or in the convolution example of 3 by 3. We only use 3 by 3 filters in every block, in every layer. And what we have done was we generated 3 stages. Each stage had a convolution stage and a max pooling stage, followed by a nonlinear activation, so a reloop, or rectified linear unit. And from depth to depth, we added more hidden layers. Why? Because we wanna find out how many hidden layers are necessary to solve our problem, to have the best performance for our problem. This was the reason why we have done this kind of experiment. So we added layers from experiment to experiment. And we not only added layer, we also added neurons. So this means we not only invested in depth, we also investigated the width. So how many neurons per layer makes sense? How does the result change when we add more neurons in each layer? And without going too much into detail, or let me show you a little bit of the results. So what we investigated here was how will depth influence the detection results? So the depth is the number of layers. How will the number of layers influence the detection results? And what you can see here from the basis to depth 3, that the basis have, I think, 3 convolution layers, depth 3 have 9 convolution layers. We only have a performance gain of 1.4%. So this means even if we have at least 4 times more convolution layers, we have just slightly a little bit more, slightly bigger performance. And what is very interesting is that in the basis network, the number of parameters, the number of neuron weights is approximately 7 million. So 7 million neurons we have to optimize. In the DEF3, so in the network with much more layers, we only have roughly 4 million neurons. Why? Why does a larger network have less parameters? Because the point or the position in the network where the most parameters occur is exactly where the convolution ends and the neural network decision function begins. And because in the basis layer we end up with a much higher dimensional feature set compared to the DEF3 set, we have much more parameters in the basis layer. Okay, one thing was very important for us, or what will this tell us? So my suggestion, and maybe you have a different one, is why does it not make sense to add so much layers? Because I think in defect detection we have one problem compared, for example, to people detection. The problem is in many cases not complex enough. So this is a scratch. And what is a neural network doing with all this data? It transforms it from low-level features to very high-level features. But the object we want to describe is a scratch. And you cannot transform this very easy geometry into hundreds of layers. So it will simply vanishing. So the problem is in some cases not complex enough. You can also investigate the width, so this means the number of neurons in each layer, and here it is a little bit different. By adding more neurons, we can gain plus 5% in performance, and this is a huge step. Nevertheless, if you compare all these different kinds of networks, the best network basically is this network, or I would choose maybe this network because it has the biggest performance. But if you also take the runtime into account, maybe the network with the highest depth and the highest width will win at the end. So we also benchmarked and compared our work, which is this one here, and compared it to existing work. And in red you see where our network is definitely the best. In black, or the black stuff here, for example, is not red because other algorithms are also able to solve this class of 100%. So the basic information here is this network has no idea that it is used for defect detection. It only learns from raw data. That's all. The network has no clue what it's doing. These algorithms were specially or only created for defect detection. And this is, from my point of view, the beauty. The deep net only learned from data. That's the only thing the network knows. The other stuff was hand-coded, engineered, and things like that. And the network won. And this is a very cool thing. So here you see some examples. So these are examples the network had not seen before, and I marked it here with red. So you see it is very reliable, as you also see in the numbers. These are just some visual information with respect to that. So let me conclude a little bit, or let me finally conclude. So what we learn is, or what I want to say is, deep learning pushes machine learning to the next level. Why? Because in old style machine learning, we care about the raw data. We shift pixels around. We shift basic information around. And what deep learning is doing, or in contrast to that, in deep learning, we only create architectures, and we don't care about the low-level features. We don't care about the pixel values. We only care about the architecture. Find an appropriate architecture to solve a given problem. And this is, from my point of view, the next level in machine learning. And one thing is very important when to choose deep learning. So first of all, you need enough training data. It is not so important if you have labels or not. At some point you need a label, but you need enough data. The next thing is you need massively parallel hardware power. So I'm a fan of NVIDIA, so I highly recommend NVIDIA. You need NVIDIA GPUs to do deep learning. There are a lot of frameworks around. I don't want to recommend one of them. I mean, TensorFlow is a famous one for QDNet. I don't have really a recommendation. depends on your problem. And how does the problem have to look like that it is appropriate for deep learning? Basically, why is deep learning so important for image processing? Because images can be processed in an evolutionary way. So for example, if you do face detection, remember the face example, you first of all start with some low-level pixel features, and then on top you learn nose, ears, and things like that, and finally you learn complete faces. This is the evolutionary trend of features. If you have a problem like this, deep learning is perfect. And it also makes sense to use deep learning when the manual feature representation is saturated somehow. You do not gain more performance with adding more features, then also add deep learning and see what happens. And from my point of view, this is the most important picture of that talk. Deep learning scales with the data, and this is from my point of view extremely important. So if you have any questions, I try my very best to answer them. Let me just add one comment. If you are searching for a job, if you are searching for a PhD, if you are searching for a student job or whatever, we hiring like hell. And feel free to send me your CV or whatever you want to my email address. Thank you very much for your attention.
Thank you.